Hello, I'm Brigham Campbell, and this is my 8-bit breadboard computer, which I'd like to introduce to you. So I'd like to start this video with a bit of backstory to the project and a time-lapse of the build process. I started this project several months ago when my employers at Niatec purchased several kits for the small breadboard computer online. They graciously extended an invitation to me to take one to my apartment to assemble it. When I return the assembled kit, they plan to frame it and use it for educational purposes there. I hope it can be a useful asset to the folks there, but I know I've already gained a ton of knowledge from it simply by assembling it. As an aside, I do not officially represent Niatec, and they did not request that I make this video. So, before starting the project, I had a pretty basic knowledge of the theory behind von Neumann computer architecture, which constitutes shared memory for programs and data, one bus for accessing memory, and a control unit, among a couple other things. I'd also acquainted myself with assembly and basic machine code in my many antics with reverse engineering old game console peripherals and their respective protocols, as well as carefully orchestrating some basic Hello World programs for the Game Boy with a hex editor. These things really gave me a pretty good jump start going into the project, but assembling it really bridged the gap for me by teaching me how to go from discrete logic, loose wires, and a clock signal to a working Turing-complete computer. I've always loved learning more about the interaction between hardware and software, and I believe the things that I've learned by assembling this hardware have prepared me to write more secure, stable, and performance software. Now, the kit that I was given to assemble was actually organized by Ben Eder, a great educator and computer engineer. He spent 2 years working on organizing these kits, which are accompanied by a large collection of YouTube videos, which explain the build process and design choices. His work is really impressive, and with his videos I could have assembled and debugged this computer with significantly less experience than I had before starting. He's currently working on a series of videos in which he builds a simple 6502 base computer from scratch. So if you find this video interesting, please check out his as well. So regarding the actual different parts of this computer, I have tried to label some of the outputs, which may be a little bit difficult to read in this light, but I'll try to go through each major module and explain a little bit about what's going on here. So we'll just start with the top right here. This is the clock signal generator. It tells pretty much every other module when to do certain operations, and most of the modules actually do their operations on the rising edge of the clock. So when this light comes on is when the modules are performing operations that they're being told to do. Although one exception is this portion right down here, which is actually powering the different control signals. And so what happens here is this actually outputs the control word on the falling edge. And the reason for this is because we actually need to tell the different modules what to do before we tell them to do it. Otherwise it's a little, it's kind of undefined what the module is going to do. So now we'll move on to the memory module here, which sits directly below the clock. It's actually connected to the bus in 2 different ways. Firstly, it's connected through this memory address register here, which is just connected straight to the 4 least significant bits of the bus. Secondly, it's connected through the memory contents here, and this part can actually be read to the bus or read from the bus to store into memory. And actually this module is a little bit more complicated because it's where our program is being run from. So once we power up the computer, we have to switch into programming mode, which I actually have on right now, indicated by this red light. And then we use these 4 dip switches to navigate to each address that we want to program. And then we use these 8 dip switches to program the actual contents of memory that we want. And then this push button right here to program the value. So I can change, because I'm in programming now, I can change the current value that I want to something else, and then I push the button, and then the contents show up right here at address 0. And actually this module gave me a couple issues, which I will go into further later. And so moving along, we have here the instruction register, which is fairly simple. It just connects straight to the control logic, and its purpose is to tell the control logic which instruction we're currently working on executing. So at the beginning of each instruction, the control logic here loads the program counter into the memory address register, and then loads the corresponding memory contents into the instruction register, and then executes the instruction from there. And actually, only the 4 most significant bits here are connected to the control logic, which means that our instruction set is limited to 16 different instructions. And the 4 least significant bits here are just data. And pretty typically, they correspond to a memory address at which we are performing some sort of operation, either reading into a different register or writing into. And so right up here, we have the aforementioned program counter, and its sole purpose is just to keep track of where exactly in the memory we are currently executing our program. So as explained before, at the beginning of each instruction, its contents are loaded into the memory address, and then it's incremented just by 1. So it's pretty simple. And then just below it, we have the different registers and ALU. And these are pretty simple as well. The A register and the B register, these each can be read into, but only really the A register currently can be read out from. The B register doesn't really support that right now because we're a little bit short on the control signals to do that, because we've already populated actually 16 control signals, and that's all we have available to us with this combinational logic here. And the ALU, which is just sandwiched between them, supports addition and subtraction, and it's really pretty basic. It only inputs from these two and then can only output from the bus. And actually sitting right next to it are the carry flag and 0 flag. And what the carry flag does is it tells us when the summation between the A register and the B register actually result in a overflow. So say if the A register had 255 in it and the B register had 1 in it, then the value would actually become 256, which can't really be represented by an 8-bit computer. So it would result in an overflow, and the ALU would output 1, and the carry flag would be set. And this 0 flag right here just tells us when the summation of these two registers is 0. And next up we have the output module here below the registers and ALU. And the purpose of this one is really just to output some values and be able to read them in decimal instead of binary. And you can see here we actually have a jumper wire which lets us control whether we're viewing in unsigned or signed 8-bit mode. And so right now it's outputting -1, which may be a little bit difficult to see. But if we switch this to low, then we can see it outputs 255, which corresponds to -1 in 8-bit signed mode. And finally we have right down here the control logic, which I talked a little bit about before. What it does is it pulls information about which instruction we're currently executing, as well as which micro-instruction step we're currently on. Because each instruction is actually split into smaller micro-instructions, which are really just combinations of these control signals, either being high or low, telling the computer what to do. And this module is actually probably the one that I understood least when I started this project. It's what really couples all of the modules very tightly, because each module is very loosely coupled through the bus, but they're all very highly coupled through the control logic. So now that we know a little bit more about the hardware, let's go through programming, assembling, and running a program. Now, the actual instruction set that's available to us consists of these instructions here. So we'll just organize a very, very simple program that will increment our output here just by 1, and we'll just loop forever. So it'll start from 0, and then it will count to 255, and then it will loop back to 0 and just repeat forever. And so to do this here, I've written this program, and hopefully you can read that. It's a little bit small, but at the first address here, we load the immediate value of 0, and we're going to load that into the A register here. And then we continue onto the first address, which says add the value at address 15 into the A register. And so that will take the address 15 and then take the contents of that address and then put it into the B register. And then it will take the summation from the ALU and then put that into the A register. And so then after that, we say output to the output module, and then jump to 1, which will set our program counter to point to address 1, which will repeat this process here. And so then finally at our address 15, we will have just a value of 1, so that when we add the value at address 15, it will pull that 1 and increment A by 1. So to be able to go from these mnemonics, which are text readable by humans, we have to go through a process called assembling. And in like some higher level languages such as C and assembly, we have assemblers which actually do this process for us. They take assembly code written in these sorts of mnemonics, and then they convert it to bytecode, to machine code. And so I've done that process manually here, and as you can see, we have these different addresses right here, and then we have the values that will be at these addresses on the other side. So at the 0th memory address, we have this value 01010000, and that corresponds to load immediate right here. And then our data half of the opcode is just filled with zeros. So that means load the immediate value of 0 into the A register. And similarly for our first memory address location, we have 00101111, and that correlates to our add instruction here. And instead of actually adding this immediate value of 15 here to our A register, what it does is it looks up the value of memory at this location, which in this case is 1, and then it puts it in the B register and then adds it. And the reason it does that is because we can only really store 4 bits in here, and it's actually an 8-bit computer. So if we can't really use 8 bits of our computer, then there's really no point in it being 8-bit at all. So we just use this to reference memory. And then once we've done that, we output it, and then we repeat with this jump. So let's go ahead and program it in. We'll just set this to 0, and then we'll switch to programming mode. So at our 0th address, we want to program in this value of 01010000. Okay, yeah, so we have that. Then we go to address 1, and we get 001011. Program that, and then move on to the next one. Good, move on to the next one. Good, and then we move all the way down to address 15. And we're just going to put 1 in there. Okay, so we should be ready to go. We'll just switch back to run mode, and then we'll reset all of our registers, and it should start. I'm just going to speed up our clock here so we can see what's going on. And yep, it looks like it's working. If you can see that, it's a little dark, but it is incrementing our output by 1. And then actually, if we speed it up even more, we'll be able to see it overflow pretty soon here. There we go, that's a little bit better. Yep, so it wraps around to 0 and then just starts again. So now we've talked a little bit about the hardware of this system and the software and programming. And now I'd like to talk a little bit about some issues that I had while building it and some changes that I'd like to make if I had the chance. So I talked a little bit about earlier this memory module and how I had some issues with it. And specifically it was this portion right here. And this chip right here is a NAND gate. And the purpose of this chip is to mix the clock signal with the memory in signal, which writes to memory the value on the bus. And specifically, there's a little capacitor resistor circuit right here, which detects the rising edge of the clock. So I was having issues with this because when I plugged in this CR circuit, there are actually certain modules across the computer that were recognizing the clock to be twice as fast because of noise that was actually introduced by this circuit here. So the fix for that was pretty simple. What I did was I just I fed this clock signal through 2 inverter gates, and then that pretty much just isolated the signal, and then I fed that isolated signal straight through this capacitor resistor and to nothing else to make sure there was no interference beyond that. Another issue I had though was right down here with the instruction step. You see these LEDs should be lit as well by a 3 to 8 multiplexer, which would normally go here. But I was getting issues because when I plugged in the IC here, it really didn't behave as expected, and it would heat up and get really, really hot. And I think the issue there was that the power distribution of this system really isn't super reliable, and the tolerances on that IC seem to be a little bit less forgiving than a lot of the other ICs here. So what I did is I just completely removed that because it's actually not necessary. It makes execution much more efficient, but it isn't actually necessary at all for this computer to function. So I just removed it entirely. And in fact, if I were interested in making it more efficient, I probably would skip this entirely and actually just add another control signal here to tell the instruction, the micro instruction stepper here, when it needs to reset. So not a really great solution there yet, but hopefully one in the future if I'm able to implement one. So now, regarding some potential changes I'd like to make, I think the biggest limitation of this computer right now would have to be that there's only 16 bytes of address space available to it. The sorts of programs we can make here are really not very complicated, but if I could upgrade this memory address space to 8 bits instead of 4 bits, that would actually increase the memory from 16 bytes total to 256 bytes total. And I think that I could make some much more complicated and much more interesting programs with that. So I'm actually going to get my own kit, which will be identical to this one, and I'll be assembling that. And then later on, I'll hopefully be able to make these changes, upgrading the address space, and then adding a couple other control signals, specifically one to reset this micro instruction stepper. So that's really all I have to say about this computer I've built. I hope you found this video interesting, and if you have any questions, suggestions, or comments about this project, please leave a comment and I'll try to respond quickly. And if I see some interest here about the upgrades I have planned, I'll be sure to upload a follow-up video as soon as I can. Thanks for watching.